Hey everyone, in this activity we're going to cover fundamentals of functions in R. So first we'll talk about how we can create our own custom R functions, how we can use conditional statements to conditionally execute code if a certain Boolean value is true or false. We'll talk about how we can use warning and error messages to better inform users of our functions or ourselves in using our own functions. We'll talk about optional arguments and required arguments when we create our own custom functions, and best practices for when to use optional or required arguments. We'll talk about local and global environments and how those are important considerations when working with functions, especially in the debugging process. And we'll talk about how to work through or troubleshoot when there's issues in our code, essentially debugging of functions in R. So functions in R are a great aspect in that they allow us to bring our own personal style or approach to coding and allow us to have more organized code more generally. So it increases reproducibility. It's easier for others to reproduce the same results that we've obtained, and also just reduces the chances of issues or bugs in our code. So conventionally, uh, without functions, it may be tempting to copy and paste similar blocks of code that you then tweak slightly to do something new or slightly different in the future. This is a nice, quick, easy fix that can work well in the short term, but often if you find yourself copying and pasting code with slight tweaks each time, ending up with 2 or 3 variations of very similar code, what can happen is when you need to update things or fix things that you found are an issue, it can be very tedious to then update all those similar blocks of code that you've copied and pasted. So you can quickly find yourself in this setting of a very messy kitchen, a very messy programming space, right? Whereas when using functions, we can implement similar code with slight tweaks of it by using arguments in these functions that can be either required or optional. And this allows us to keep one consistent space where we update the code, making fixes or extensions for it. And so we end up with a much more organized space, making it more efficient for ourselves to read our code and understand it, and also others who might be using our code or function. Okay. So it's a little bit more upfront work to do functions, to use functions instead of just copying and pasting. But in the long run, it pays dividends over time. So ideally, when we create functions in R, just like R objects, we should use a descriptive name that clearly communicates what the function is supposed to do. This helps not only our future self, but others who might end up using our code, right? You might always envision yourself as being the only one who uses your code in your job, but inevitably you might get assigned a different task or project and somebody needs to take over for you, right? And so it's always useful to have readable, descriptive comments and names in your code. Functions ideally save us time, as I mentioned, because we only have one place we might need to make fixes if we find issues with how our code was written, as opposed to the copy and paste approach, where we would need to then sift through and find each instance of the modified code and update the bug or the issue. Um, so it can be easy to miss one accidentally or not update it properly when using this copy and paste approach. So functions ideally save us time in the long run. Okay. So this not only makes it faster to fix our code and to progress forward, but it just reduces the chances of mistakes or bugs occurring in our code because of less places we need to update. All right. So let's start by getting RStudio opened up here in a new file. And we're just going to need the tidyverse for this activity. And I'll suppress warnings and messages myself just because the tidyverse especially can have a lot of messages when starting up. Okay. All right. So let's look at a basic function to start here. One that calculates the sum or adds two numbers. Okay. So here we're defining our own custom function called calculateSum. We use the arrow assignment operator to create a function, and we put function with the arguments separated by commas in the function definition, and then the body of the function, which can consist of one or multiple lines of code. It's best practice to enclose in curly brackets here. Okay. Typically, functions end with a return and that they are returning some value or object in R. Although it's not always the case that functions return something. Sometimes they just execute some type of action, but most of the functions will use return a value or object. Here, this calculateSum function is returning the sum of these two numbers, number 1 and 2. Okay, so let's copy this code. And let's make our first custom R function. Okay, so when we run this code, we are calculating the sum of 5 and 3, and we get the result 8. Notice that we can implicitly specify the function arguments by just separating values or objects by commas when calling the function. In doing so, R will default to the ordering of the inputs or arguments in the definition of the function. So when we don't specify the argument names explicitly, it assumes 5 is being supplied for number 1 and 3 is being supplied for number 2. We can also explicitly specify argument names, which is likely a better approach in many situations, and that gives us the same result here. Okay. So similar to R objects, when we create a custom function, this will appear in our environment pane. Okay, over here. So you can see we have this section for functions now after running this code and defining that function, and it exists right here. Okay, calculateSum. So let's use calculateSum to calculate the sum of 13 and 1989. Okay, see if our function works. We should get 2002. We got 2002, nice. So here we're again explicitly listing out the argument names. Okay, but note that and in the natural ordering is how the function was defined. R does allow you to call arguments in a different order. Okay, so here we're specifying number 1 first, number 2 second, but note that R would allow you to say specify number 2 first and number 1 second. Okay, we get the same result here, and either way is valid. Okay. Typically you would follow the order in which the function was defined, but if you list out the argument names explicitly like this, you can do it in any order. R has some flexibility in that regard. You can also call functions by explicitly naming some arguments and implicitly supplying values for other arguments. What that will do is at first we'll assume, okay, 1989 is for the number 2 argument. And then since 13 is supplied without an explicit argument name, R will assume, okay, it must be the first argument in the function definition that's not number 2. And so in that case, that only leaves number 1. So 13 would get supplied to number 1 here. Okay. So R has lots of flexibility, different ways in which you can call functions when using them. So let's think about what happens when we calculate NA, the sum of NA in 1989. Okay, so if we calculate the sum of NA in 1989, we get NA. NAs are contagious in R generally. And our function doesn't throw an error, it just essentially tries to calculate NA plus 1989, and that's what we get here. Okay? So if we don't like that behavior, if we wanted it to throw an error or give a warning, we could code that into our function to have more complex behavior, but as it stands, it's simply just giving us NA back. So let's talk about some best practices when defining an R function. Like I mentioned, we want a descriptive function name. It should be reasonably concise, but Hadley advises in his book, and I think this is generally good advice, err on the side of being more descriptive rather than concise if you're considering the trade-offs between the two. So this goes for the function name, but also for the arguments of the function. Notice here we called the arguments number 1 and number 2, rather than something less descriptive like x and y. By using number 1 and number 2, it makes clear to the user or our future self that these need to be numeric valued inputs. Okay. Also, it's best practice to write the code of our function enclosed in curly brackets and to have an explicit return if we're returning a value or object from our function. Technically, with the calculate sum function, you don't have to use curly brackets. Okay, so we should avoid this style of code. If you don't have the curly brackets, okay, this is actually still a valid definition of a function in R. It just will look on this first line and assume, okay, there's no curly brackets. The user must be assuming this one line after the parentheses here that continues on here is what is the body of the function. And so it still allows you to, we'll call this like calculate sum bad. This still allows you to calculate the sum properly. You might see this online, people defining functions without curly brackets. Again, not good practice. It's not always super clear where the function begins and ends in this way, especially if someone's newer to R. So it's just not a great practice. The explicit return is also nice because it's being clear about what the code is doing. But actually, if you don't have a return, R is flexible again in that it will allow us to not have an explicit return, and it just assumes, oh, this was something that was the last thing printed or calculated, so it must be what the user meant to return. And so again, it gives us the same result, even without the curly brackets and without an explicit return. Okay. Please don't do this. Not great practice. Okay. We want to have curly brackets whenever possible. No reason we should be missing curly brackets. And then if our function's returning something, it really should have an explicit return. Okay. So I'll keep the bad function definition there. All right. So Hadley-Wickham also advises naming functions using verbs rather than arguments, rather than nouns. Okay, and same with the arguments, he advises nouns rather than verbs. So for example, here, notice that our functions, okay, start with a verb, calculate. That's what they're doing. It's an action. And the arguments or inputs are nouns, number one, number two. That's just Hadley's view on things, and I generally agree with it, but certainly whatever your own style is works fine. I would say consistency is key, right? That's what's most important, I would argue. So how can we be consistent in our function names? Well, R is case sensitive in the definitions of objects or functions. So we can define things using camel case, where we separate words using capitalization. We can also use snake case, where words in the function or argument names are separated with underscores, right? Those are the two most common ways. I would just say if you're using one approach, try to consistently use it, right? When I first started coding in R, I really liked camel case, but on a rare occasion, I would sneak in some snake case in my functions or object names. It's not a good habit to intermix the two, I would say. Try to consistently stick with one. It just makes your code more readable, easier to understand what's going on with it. Yeah, this graphic from Dr. Allison Horst nicely shows how you can have snake case, camel case. Kebab case doesn't work for R right out of the box super easy. You would need to enclose this in backticks. But you could use screaming snake case, essentially all uppercase snake case. That's an option for sure. Okay. But generally, I would recommend using either camel case or lowercase snake case. Good practice. Another good practice is that when you have sets of related functions, it's a best practice to name them in a somewhat connected, consistent, informative way. So one way to do this is to use a common prefix to show that those functions are related. That also helps with tab to complete, in that if you're trying to call one of those related functions in RStudio with a new enough version, which most of them are now, or another IDE, you can use that tab to complete in a nice way. Okay. So here's some examples of functions that are poorly named. We've got fun1 that takes x and y and adds them together. Very similar, essentially the same as our calculate sum function from before, but because it's named not descriptively in terms of the function name or the argument names, it takes slightly longer to understand what this code is doing, right? And similar for another function, fun2, where we are calculating the difference or subtracting two numbers. So instead, we want to opt for this approach of using a verb. We're using lowercase snake case, right? Calculate sum, and we call our inputs nouns that are descriptive of what those argument values should be expecting, right? Numbers in this case, numeric values. Notice how we also have a single comment right above the function definition. This is best practice as well, to have a comment briefly describing what your function's doing or what you're creating here. Other small things to mention real quick that you want to avoid when defining functions or other objects in R. Try not to avoid special R functions or objects that already exist. Okay. Because R will let you do so, and it doesn't even give you an error or warning at all. So this can be a little bit tricky. So for example, in R, to mention some of the most common examples of this mistake, in R, the Boolean value true is true, all caps, but you can also have capital T, and that also represents the Boolean value true in R. Similar with false, okay, and F. R will let you overwrite capital F or capital T with your own object or function, or even true or false. And that can mess up code in other ways if you're referring to these Boolean values, but trying to refer to the true false and not the object you created. Okay. So for example, you can actually overwrite the object capital T with false, and that can make things, right, all kinds of issues in your code. A common one that's easy to accidentally do is naturally you might create a variable called lowercase a, and then lowercase b, and then lowercase c. But lowercase c is a very important function in R. It's a base R function that allows us to combine values into a vector. Okay. So we don't want to overwrite that with like a constant value or something else, right? We want to reserve that C for the function name from base R. Okay. So these are just some quick best practices, some common mistakes to avoid, but in general, you will certainly learn as you go as well, in that some of these things might cause you headaches, right? For me personally, this overwriting of C caused me a headache one time because my code was returning an error. I didn't understand why, because it was syntactically correct, except I had accidentally overwritten lowercase c much further up in my code, and that was causing issues that cascaded on down. Right? So hopefully you can just avoid those entirely yourself. All right, let's look at this utry part here. So let's read the source code for each of these three functions below, which are not named descriptively, and try and decide what these functions do. Okay. So go ahead, maybe hit pause on your video, try and think about these functions on your own, what they do, and then we'll chat about it together. All right, hopefully you had some time to think about it before we chat about it. So here, f1, our first function that we're looking at here. Let's think about what this function does. A helpful way to explore things might be to try this function out. Okay, so for example, let's say we have a word like preclude, and we want to see if it has the prefix pre. Okay, this returns true. It's finding that pre is at the start of this, but notice that if we have something that is contained in the word, but doesn't come at the beginning, does not find that to be true. So a better name for this function might be something like check prefix or contains prefix, right? That would allow the user to much more quickly decide if or understand what this function is doing exactly. Okay, so in addition to a descriptive function name, a comment above this would help significantly as well. So maybe something like create function to check if a string starts with a given prefix. Okay, already this code is much more understandable, significantly improved from how it was defined before, and we can also add in an explicit return. Okay, so what this is doing here is it's extracting a substring from the provided string, starting from the first character through the nth character, where n is the total number of characters in string, and checking if it's equal to the supplied prefix. Okay, much better. So the function provided checks if an input string starts with a given prefix. All right, let's look at the next one. F2 here. So since x is the input to F2, and it's just called F2, it's really not even clear what type of value or object we should supply to this function, right? There's no comment, there's no descriptive naming. It's not a great way to define a function here. But notice if we supply a vector of the numbers 3, 4, 5, it returns 3 and 4. Or if we supply just the number 7, it returns null. X can also be character string values. Okay. So what does it look like F2 is doing here? It's dropping the last item or entry of a vector when given a value. But if there's a single value provided, it just returns null. Okay, so a better way, more descriptive way to name this might be like drop last. Okay. And giving a descriptive comment. Create a function to drop the last component of a vector. Maybe instead of x, we call it my vector, something like that. You could call it just vector, but note that vector is actually a function from base R. Another way to create a vector besides just lowercase c. So I try to avoid that. One way to do it is just to call things my underscore something. Okay, and then for what this code is doing, first what it's doing is it's checking if the number of components or entries in X is less than or equal to 1. If that's the case, it's saying return null. Okay, and then we could even add in an explicit else. And ideally, this should have its own return as well. That's essentially what was implicitly happening before. So if the length of x is not less than or equal to 1, in other words, if the length of x is greater than 1, it's going to return x, but dropping the last entry of x. Okay, this syntax is using base R syntax, in which if you have a vector in base R, you can drop the last entry of that vector using square brackets and then negative indices to do so. So what this is doing is it's calculating the length of x, that might be 3, And so this will end up saying -3 in here, and that says drop entry 3 in X. And since we renamed it to myVector, we will have to update X to be myVector throughout this code. Okay, as well as in the function calls below. There we go. And we'll also update F1, or I'm sorry, F2 to say drop last. There we go. Much more clear what our function is doing here. All right, let's look at the last function that we have here. So here we've got X. Again, vague, not descriptive in terms of what type of input this should be, which is not ideal. And even the function name called F3, not descriptive either. Worse yet, when you call this function, it's not even entirely clear what this function is doing. It's calculating the reciprocal 1 over the mean of the reciprocal of each component of X. So in this case, X is supposed to be a numeric vector, so we can call it numeric vector. It's one option. Okay. And this last function is actually calculating a special type of mean that's equal to the reciprocal of the arithmetic mean of the reciprocals. Okay, this is called the harmonic mean. Surprisingly, in statistics and data science, we very often opt for what we call the arithmetic mean, the sum of the numbers divided by the total number of values we've summed. There's actually several types of means that we can use in statistics. The harmonic mean is one of the other options. Okay. So instead of F3, a better name here would be calculate harmonic mean. And we can add an explicit return. And a comment describing the function definition. Great. So the harmonic mean is useful in different settings. As the Wikipedia page notes here, it's appropriate or commonly used when working with ratios or rates, such as speeds. Okay. So different domains, different areas can use different types of means. In statistics, we just tend to favor the arithmetic mean because it has a lot of nice theoretical properties. But in other domains, other types of means are more commonly used. Okay, so let's look at one other type of mean, the geometric mean. Okay. So for the geometric mean, there's a couple different ways you can calculate the geometric mean. You can calculate the nth root of the product of all of the numbers. So in other words, if you had 3 numbers, you would multiply all of them and then calculate the cubic root of that product. The same as that product to the 1/3 power. An equivalent and alternative way is to calculate the arithmetic mean of the natural log of each number and then to exponentiate that. Either way works. Here we can use the prod function and check that out, and use the caret symbol to calculate the nth root. So try that out on your own for a minute, and then we'll look at it together here. All right, hopefully you had some time to try out making your own function to calculate the geometric mean. Let's take a look here. So one way we can do this is to calculate the product of the vectors, of the numbers in the vector using the prod function, and calculate that product to the power of 1 over the number of values in the vector. Okay. Now notice if we have this numeric vector with a bunch of big numbers, okay, the numbers 1 through 50, we can calculate the different types of means for this vector. Here we have the arithmetic mean, which is a little over 1 million, whereas the harmonic mean, about 12. And the geometric mean is about 56, 57. Okay, so very different results depending on your choice of mean. One thing to note as a side note here is that R, as with all programming languages, does have some limitations when working with big numbers, right? It can be easy to think of our computers and programs as perfect, flawless machines, right? But there are limits to how big of numbers R can calculate. So for example, here what we're doing is we're calculating the different types of means of all these numbers, where we have the numbers 1 through 50 included in here with this 1:50. Okay, there's actually only 50-ish numbers, about 56 numbers here. But if we had this include the numbers 1 to 500 instead in here, okay, still a large, 50, a little over 500 numbers in here now. But certainly something we should expect our computer to be able to calculate the means of, right? If we now try to calculate the geometric mean for this, okay, what we get is it calculates the arithmetic mean, okay, the harmonic mean, but now the geometric mean R returns infinity. But the geometric mean of this vector of numbers is not infinity. R just cannot handle the large number that ended up from the product of all of these. Okay, it was too big for R to keep track of what that was, so it just ends up saying infinity. And then what happens is it says, okay, what's infinity to the 1 over 500-ish power? And it still says infinity, right? But that's incorrect. And there's no warning or error letting us know that. So sometimes you have to be a little bit creative in how you code things, especially when working with very large or very small numbers. So an alternative way we could define this geometric mean function, for example, is to use that alternative definition that the arithmetic mean of the natural log of each number and the exponentiation of that also gives the geometric mean. Okay, so if we use that definition, instead of infinity, we get the actual value, which is only 203. It's actually not that big of a number in the end, but just in those intermediate calculations along the way, R loses its way using the product approach. Okay. And to show that these are the same, okay, if we go back to when The product approach could calculate it with just the numbers 1 through 50 in here. Okay, you get the geometric mean of 56.65-ish. And you get the same geometric mean value here. Okay, but this approach can just handle larger numbers in the calculation. So just want to make that a little quick side note about the limitations of R. And this is not unique to R. Other programming languages have similar limitations as well. So that's the geometric mean. Let's move on to talk a little bit about how we can use conditional execution, warnings, and errors to write more complex functions. So let's start with conditional execution. Using if-else statements in R, we can conditionally execute one or more lines of code if a certain condition is true. If this condition is false, we can say then alternatively execute one or more lines of code instead. Right? So here we can do this, for example, if we wanted to write a function to calculate the square root of a number. Okay, if we have some input val for value, we can say if value's non-negative, it's greater than or equal to 0, return the value to the 1/2 power. Otherwise, return NaN, not a number, along with printing a warning, letting the user know what happened. So we can see how to use this function here. Okay. By trying to calculate the square root of 4 and -9. Okay, with 4, notice that we just get the value 2, but when we try to calculate the square root of -9, we get this warning in red, and then it still returns NaN. Okay, so notice that with a warning, it prints a message in red, but it still continues on with the execution below the warning, returning this NaN value. So warnings are good to use when you think something might be a problem based on what you're seeing in the code, based on what the function sees, but it's not egregious or serious enough to consider halting the execution altogether. You're just printing a message, but still allowing the code to continue executing. Right? Errors, on the other hand, are considered more serious. So if you see an issue in the code based on what the user input that you consider significant enough that it must have been a serious mistake, you can halt the execution of the code and print a message to the user letting them know what went wrong. Okay. Errors, you might think the function would be called error, but actually the function's warning for warnings, and it's stop to make an error occur. So let's modify this calculate square root function, but this time to use an error instead of a warning. Hmm. Instead of warning, we say stop. And now notice when we run the code, okay, we get an error. It's red. We get the value of 2 when calculating the square root of 4, but now we don't get NaN when trying to calculate the square root of -9. It just stops, and it says error, val is negative, but must be greater than or equal to 0. Okay. So again, it's your judgment call depending on what you see and what you're checking for, if you consider it egregious enough to use an error or just a warning or anything at all. So we saw how we can use a single if and else statement. We can also chain multiple if statements and else statements together if we have several possible conditions that might be true. Okay, so if condition 1 is true, we can execute one or more lines of code. If condition 1 is false and condition 2 is true, then we can execute this code. And if condition 1 is false and condition 2 is false, then we can execute this final piece of code. Okay. So keeping this in mind, how we can use this structure of conditional execution in R, let's try another part on our own here. Okay, let's make a function called is underscore whole number. That will check if a number is a whole number or not. Then using that function, we'll make another function called raise power that has two arguments, value and power, that raises a specified number to a given power. We'll return a warning and an NaN value if the number is negative and the power is not a whole number. So for example, if we try to calculate the square root of -3, our function will return NaN and a corresponding warning. Then we can use our function to try and calculate 4 to the second power -9 squared, the cubic root of 3, and the cubic root of -3. Okay. So take a minute to try these out on your own. Pause your video, trying them out, and then we'll look at it together. Okay, so let's take a look at how we can make this function is whole number, which will return true if an input number is one of the non-negative integers, 0, 1, 2 on up, and false otherwise. And we'll just assume that our function inputs a number, okay, correctly here, not like a character string from our user. So there's several ways you could do this here that are correct. One way is to use the modulus operator. Okay, the modulus operator essentially allows you to get the remainder after dividing two numbers evenly into one another. So for example, if we have 10 mod 5 in R, where 2% signs give us the modulus operator, this returns 0 because 5 goes into 10 evenly 2 times, and there's no leftover remainder. But if you did 11 mod 5, you get 1 because 5 goes into 11 twice, and then you have 1 left over. It's kind of like division back in elementary school when we would calculate the remainder that's left over. You can divide any integer or do any integer mod 1, and that will give you 0. Any integer mod 1 is 0. Okay. Even negative ones. So what we can do here is check if a number mod 1 is equal to 0. Okay. And initially screen out all negative numbers. Okay, so essentially if a number is negative, we just return false no matter what. And so then we're assuming that a number is 0 or greater, and in that case, we want to check if it's an integer. So one way to do that is to use number mod 1 and checking if that's equal to 0. Note that there is an is.integer function in R, but this is not as good of a way as using the modulus operator here, because it can be prone to um, thinking something's not an integer when it actually is, just due to precision floating point issues with R. Okay, so it can be kind of hard to reproduce, but for example, we know that like 1 is an integer, but oh, actually, I got it right off the bat there. Is that integer around just the number 1? It says false, but 1 is an integer, right? And we know that 1 mod 1 is equal to 0. So this is a more consistent way. So what happens, like why this returned false, is because R in the background, even though I typed 1, it really has this stored as like 1.00000 with a bunch of zeros, and then maybe like 16 decimal places out, there's something that's slightly different than 0. So R has a hard time determining that that's exactly an integer. One way to avoid that issue, if you did want to still use is.integer, is that in R, if you put an integer value and then capital L when you're manually typing out the number, that tells R, hey, don't assume anything far out in the decimal places that's non-zero. Just recognize this as a valid integer, right? But that can be difficult to do because you need to have the number written out explicitly. It can't be like an object being supplied to our function. So if you have capital L after like an object name, that just would not work. So this modulus approach is more general and in the better approach here. Okay. So here we used a combination of different if-else statements to consider different conditions for whether or not our function is a whole number. And we can see how this works, right? With -1, it should return false. Because it's negative 1/2, it should return false because this is not an integer value. Okay. And then testing that floating point precision issues, right? 1 divided by 1 should return true. And we do see that that's the case, whereas using is.integer can be tricky if we had used that approach here, right? Is.integer, if you do that around 1 divided by 1, yeah, returns false. It has a hard time with that. Okay, so our approach of using the modulus operator is better. All right. Let's look at the next part now. The caret operator raises a number to a specified power in R. So we're going to make a function here called raise underscore power that has 2 arguments, value and power, and that raises a number to a specified power. And we want to return a warning and an NaN value if the number is negative and the power is not a whole number. So what we're going to do here is we're going to create a function called raise power, but we're going to actually use the function we defined previously, is whole number, inside of our new function definition. Okay, and how we can do that, we have raise power, value and power, and we simply call is underscore whole underscore number within our function here. So we're checking if it's not the case that power is a whole number, and it's also true at the same time that value is less than 0. We want to return a warning. And here what we're doing is we're using the string underscore C function to create a very informative warning, where we're literally inserting the power, the value of power, and the value of value inside the warning message, letting the user know, hey, power, which is this, and we're just rounding it to 4 significant digits, must be a whole number if value, and then we even give what value was given as negative. Okay, and then we still return NaN. Otherwise, if that's not an issue, we just return the calculated value to the power of power. Okay. And we can test this function out, raise power, on some numbers here. So we're going to calculate 4 to the second power, which we know should be 16, minus 9 to the second power. So we can think about, is that going to give us NaN, or is it going to give us a valid number here? Minus 9 squared is 81. Yeah, it should be a valid number. And we can call things in a different order again. So 3 to the 1/3 power. It gives us the cubic root of 3. I don't know that exact number. It's an irrational number, right? But it's somewhere between 1 and 2, about 1.5-ish, 1.4-ish. And then we can calculate a cubic root of -3, or at least try to. Although here, power is not a whole number and value is negative, so this should return NaN. So we get the cubic root of 3 is about 1.44. And then for the last part here, stemming from power being 1/3 and value being -3, here we have a warning letting the user know, hey, you gave a power of 0.3333, which must be a whole number if the value is negative, which is the case here. Okay. Note that technically, mathematically, we can calculate the cubic root of -3. That's minus 1.44225. That's the cubic root of -3. But in R, if you try to do this, even without our function, just using R itself, R can't handle that. So again, another limitation of R, note that it can't calculate cubic roots of negative numbers well, even though this is totally a valid, well-defined number, mathematically speaking. Okay. So you just have to be aware of some of R's limitations sometimes when working with it. Let's look at another U-try part here. Okay, considering this modulus operator again. So 10 mod 3 is 1 because 3 goes into 10 3 times with 1 remainder. 10 mod 2 is 0 because 2 evenly goes into 10. 10 mod 5 is 0. All right, considering the modulus operator here, let's make a function that will check if a number is even or odd. Be careful when copying some of this over. You won't want to copy what's next to the square brackets yourself, or else that will give an error. Notice how I'm just selectively copying some of these pieces over. All right. And you don't have to copy this over yourself if you don't want to, but just showing it here. And then we can calculate those ourselves. Okay. So take a minute, pause your video again, try and make your own function to check if a number is even or odd using the modulus operator here. All right, so here, hopefully you had some time to try it on your own. One way to do this, again, there's multiple ways though, is we can make a function called check, even or odd, input an integer value. If something mod 2 is 0, then it must be even by definition. If something mod 2 is equal to 1, then it's odd by definition. And otherwise, we can say not an integer if we wanted to consider that as a possible situation. Okay. Notice that here, what we've got going on, for -2, it correctly identifies that it's even. For 0, it correctly identifies that it is even as well, by definition. Even, odd. 1.1, it says not an integer, right? But now we've got the case that if we try to give it a vector of numbers, our function doesn't like this, right? So what happened here is that in this condition, okay, with if-else statements like this, it wants a single Boolean value, right? But if we check something mod 2 being equal to 0, what happens if we give a vector for my integer? We get a corresponding vector of Boolean values, even, odd. But again, if-else statements can only handle single true-false values at a time. They can't handle vectors of true-false values. So we have to tweak our code if we want to use a vectorized approach to these, to checking if a number is even or odd. Okay, and so one way to make our function vectorized is to use the if-else function. Okay, the if-else, if_else, and case_when functions can all be used to conditionally return values based on a vector of true or false values. Okay, so for example here, we can use the if-else function to say, if my integer mod2 is 0, return even, otherwise return odd. And we're just going to assume there's an integer input here. Okay. Now what this will do is return even, odd. Notice that here it does still return odd for this number, although technically it's not an integer, right? But for this vector of integer values 2, 4, 5, it does correctly return even, and odd. So with if-else, just a single if-else can only handle two possible values to return, even and odd. Okay, but what we can do is use the case when function to consider more than two cases. So we can take this function, tweak it such that we can say case when instead, when my integer mod2 is 0, we return even. And we use this little tilde symbol in here. We can say when my integer tilde 2 is 1, we say it's odd. And then in all other cases, we'll say return not an integer. And that's how the case when function works. We can get rid of this approach here. Okay, and now it correctly says not an integer for that 1.1 case. So to explain this case when code again, we've seen it once before, but to the left of the little squiggle symbol, the tilde, we construct a Boolean condition that should return true or false. Here we're checking if the integer mod2 is 0. In that case, we're saying return even. If this is false, it will then look at the next condition working its way down. So now it says, okay, is the integer or the number mod2 equal to 1? If so, then it's odd. And if that is false as well, so if this first condition is false and this one's false, then what we're doing is we're just artificially making a catch-all condition, something that's always true, by literally putting the value true. It's typically considered best practice to have your final case be something that catches everything, a catch-all. And there we'll say not an integer. Okay, so that's exactly what we did. This function is from the dplyr package. Hadley actually implements nested if-else statements, although he uses the if_else function, which is very similar but can handle NA values slightly better than the base R if-else function. But Hadley implements nested case if-else functions when calling case when underneath, but case when is a little bit more readable, a little more user-friendly. All right. So other ways we can use the if-else function. If-else function is what we call a vectorized function. It can be applied to a vector of values, and it's a function from base R. So for example, if we have days of the week, in a vector along with an NA, we can conditionally return whether it's a weekend or a weekday. So we can say if it's Saturday or Sunday, return the value weekend, otherwise return weekday. Okay. And notice that it correctly identifies weekdays and weekends, but what happens is if there's an NA value that you supply to if else, it will still be considered an NA. That might be okay. It might be something you don't want to happen. Okay, so Hadley in the dplyr package kind of extended this a little bit with if underscore else, which behaves very similarly, except what you can do is you can specify the argument missing to give a value that will be supplied if NAs are detected in the Boolean condition. Okay. The case when function is a generalization of if else, okay, for more than two cases. So we used it like above to check if a number was even or odd. Okay. So generally case when, here's a very general structure, although this code won't work because we don't actually have an object defined as example data. But when you have one condition, it returns that value if condition one is true. If condition one is false and condition two is true, it will return value two, and so on. And finally, you typically give a catch-all value. Okay? And so you can use case when inside the mutate function commonly to conditionally create a new variable, but you can also use it outside of mutate like we did here, where we're just working with a vector, not a table with variables. So we can use case when in this way, for example, to determine if a day of the week is a weekend or weekday. Oh, days of week. Oh yeah, gotta define days of week first. Right here. There we go. So that allowed us to essentially even add another condition that was, right, possibly a weekday, possibly a weekend, and then TGIF if it's Friday. Okay. All right. Now let's talk a little bit about required and optional arguments. So when defining functions in R, we can make arguments or inputs that are either required, necessary to be specified by the user when calling the function, or if we have a value for the function that we think is very common, that most of the time will be used by the user calling our function, we can make an argument optional to save the user the time and effort of having to manually specify that argument each time they call our function. So to make an argument be optional in a function definition, we have to give the default value when creating the function. Okay. So it's best practice to default to making an argument required, but again, you can save your user time if you expect most of the time the user will be giving a particular value for a given argument. You can make it optional. So let's look at making a function called weekend or weekday, okay, kind of extending, looking at what we did before here. That will return whether or not a given date is a weekday or a weekend. And so this will have one required argument date, which will be deciding if it's a weekday or weekend, and then one optional argument TGIF, which will decide if we label Friday as TGIF. Okay, or if we'll still just consider it a regular old weekday. And we'll have our function default to having TGIF be false. All right, so let's take a look at our function here, weekday or weekend. So in creating our function here, the required argument date, we typically give first. So it's usually best practice to give required arguments first. They don't have anything that they're equal to in the function definition, making these something that the user must specify when calling our function. If we want to make a function argument optional, we use a single equal sign to specify a default value for that argument or input. So here we're making TGIF be an optional argument that has a default value of false. Now we're going to take a date and decide if it's a weekend or weekday. Okay, how we're going to do that? Let's walk through this function line by line. There's a few ways you could go about this. One way is to use the wday function from the lubridate package to first calculate what day of the week that date is in particular. Okay, so date might be a value of like December 13th, 1989, right? So there's a few ways we could handle this calculation of whether it's a weekend, weekday, or TGIF. Okay, what we're going to do is the approach we're taking here, but not the only approach, is look at if TGIF is true, we're going to use case when to conditionally return a vector of values that's either going to say weekday, weekend, or a TGIF. Okay. And then else, in other words, if TGIF is false, okay, we can use if else because there's only two possible conditions. Either the day of the week is in Saturday or Sunday, in which case it's a weekend, or it's a weekday. Okay. And if we wanted to consider using best coding practices, we could use our explicit return statements. Probably a good thing to do. Here we go. All right. So now we've got our function definition here. Let's test out our function, make sure it's working properly. Okay, so this first date should be a Monday, then a Saturday, then a Friday. And then if we say TGIF is true for the Friday, it should be TGIF instead of weekday. Oops. Oh, I see. We got days of week. Let's see. Oh, we've got days of week here, but it should be day of week. Okay. Day of week. There we go. Okay. Yeah, if we fix that issue in our function here, day of week. Let's see how we look now. There we go. It was referring to the vector of values that we'd made before inside our function. And that will be a nice segue into our next section where we talk about global and local environments. But for now, yeah, this should be single day of week without the S. Okay, and then that works properly where this is considered weekday, weekend, weekday, but then TGIF. All right. So yeah, the issue of when I had days of week in here, okay, what happened there is this, if this says days of week, okay, as R worked through this code, executing it sequentially from top to bottom, what happened is it creates an object within the function, okay? You can think about when we call a function in R, it's almost like it sets up its own temporary little environment with objects created in it. And the only objects that exist you can think of to start are the arguments or inputs to that function. So date and TGIF. Okay, here what happens is we created this day of week object within the function. Okay, so now date, TGIF, and day of week exist. Checks if TGIF is true, and it went down to trying to execute this case when code. Before, when I had written days of week with an S instead of day of week, that's an object that's not one of the argument names, and it wasn't created above this within the function. But R did not return an error. It was able to keep running the code just fine. So what it did is it saw an object, days of week, that didn't exist within this function or from the arguments. And so then it thinks, okay, the user must be referring to an object that's in their global environment outside of this function from before. So R will look in your global environment then, see if that object exists, which it does, days of week, because we defined it earlier up here, and then it assumes you meant to refer to this. That can be helpful in preventing errors sometimes, but it can also make your code hard to debug or figure out what the issue is if you're accidentally referring to an object outside of your function that you didn't mean to. Okay. So this temporary space that exists just within the function is what we'd call a local environment within the function. Slightly different than our global environment, which we see interactively here when working in R. Okay. The global environment is the default place for all our user-defined objects to live or reside in. Okay, so objects that we create or even functions that we create. But when we call functions, like I just mentioned, the code gets executed in what's called a local environment. Okay, so typically objects in your global environment are not going to be accessible outside of the function, or at least you shouldn't refer to them, although R does try to help you out sometimes by looking in the global environment if you call or try to use an object that doesn't exist within the function. Okay. So for example, let's look at this calculate stats function below here. This gives a vector of numbers and an argument in digits. There's some bugs or issues in this code. Okay, we can run this function, run this code, define this function. And we can look at how calculate stats when we call it. Okay, notice how within our function, there's objects created like mean value, median value, SD value. But if we call the function, these are not objects that are created over here in our global environment. There are no objects, even after calling this, called mean value, median value, SD value. These objects only existed within that local environment within the function. They're not something we can readily access or refer to in our global environment, even after calling the function. Okay, there's that separation of different spaces. This is helpful in that it helps keep our global environment less cluttered. If every time we were calling a function and all the sub objects, the intermediate objects that were created along the way existed in our global environment would quickly become very cluttered, right? However, because these objects are separated, distinctly stored away from our global environment, this can make it difficult to debug our functions if they have issues. Okay, so for example, here we have some small bugs in this calculate stats function. If we look at calculating the statistics for this vector of numbers when there's an NA value in there, saying round to 1 digit, here's what we get. The mean is calculated as 2.5, the standard deviation is 1.3, but our median is returned as NA. That's not something that we wanted to happen, but how can we figure out where to fix our code? Okay. Generally, one approach to debugging functions in R is to first create objects in your global environment that correspond to the inputs or arguments for your function, and then in the console to execute the code line by line from your function sequentially. Okay. This allows you to inspect or look at intermediate results along the way and to verify if the value of objects at each step are what you expect. Okay. If you think you found the issue and you fixed it in the code, then clear your environment out. Okay, redefine your function and try and call it again, seeing now if it performs as expected. This is sort of like the old school way, I guess, to debug a function. It works when your functions are more complex, right? Certainly nowadays as well, with the advent of AI, that can also be helpful for debugging functions, right? So here, for example, let's try the old school way first to debug the calculate stats function. And then we'll see how we can do this with AI nowadays as well. Okay. So here, let's make a copy of our calculate stats function that we're going to work through debugging here. So we keep the original one. All right. So here's what I mean. We're going to take these inputs, numbers and digits. Okay. And we're going to say, hey, give numbers this value. Okay, we're defining numbers, and then n digits we're defining to be 2. Now that we've defined these in this way in the console, they exist in our global environment, n digits and stats. So then what we can do is line by line run our code and see where the issue is stemming from. We know it happens with the median, but let's still run the code line by line. So we calculate mean value. After running that code, we can print its value here. Okay, 2.5. Is that actually the mean of those numbers? Yeah, that seems correct. Now the median value, we calculate that. It's NA. So here we can see we had this NA remove argument set to true for the mean. It was missing in the median. So now we tweaked the code like that instead. We look at the median value, 2.5. Yes, that's correct. Okay, the standard deviation also is correctly removing NA values just like we want here. Perfect. And then we saw we have n digits that we want to round something to. And we said two digits. Okay. If we look at this, Now we see median as being incorrectly rounded. Okay. In the final table, we know the issue is occurring in how the median is being stored. So here we can identify now, it's like, oh, okay, n digits is missing from the round function. So if we add that in, we can see we've correctly calculated the median and rounded it. So now this is a corrected version of our function. Okay. We can then clear things out because we want to erase all the intermediate objects that have now been created along the way. We don't want these to be mistakenly referred to when calling our function later. So it's best to clear things out with the broom icon in the environment pane. Okay. We can run all code chunks above to reload our packages, redefine everything. Oh, we had an error from before, I guess. Let's see. Let's comment that out just so that that doesn't cause us an error. Okay. Then we're going to run everything above our function definition here. Ooh, I guess we calculated it again. Yep, okay. Purposely we're causing an error before. Okay, now we seem to be good. Let's go back to the bottom. Okay. Redefine everything. Oh, another error that we were purposely looking at before. Lots of errors. Okay. Okay, great. There we go. Run everything, get everything redefined. Okay. This is our problematic function though. So we can see, here's our fixed function, debugged function now. So if we put that below the problematic definition of the function, okay, we can then correctly call our function here. Okay. So notice that we fixed two issues. We found two bugs in our function. Here's the buggy version of the function, and here's the fixed version. Okay, nowadays with AI, you can take the buggy version of the function and try pasting it into AI and saying something like identify any errors. Oop. Identify, let me get this a little bigger font. Identify any bugs or issues in the following R function. Something like this. And then pasting the function code after that. This tends to work fairly well. All right, let's see how the AI does. Okay. Yeah, that's a little bit off. That really wasn't an issue. We're actually using the correct assignment operator, but it even noted it said likely happened to do from copying from an HTML source. Okay, inconsistent rounding though. It noted it correctly identified this as an issue. It said, oh, you're not using n digits in the rounding of median, but it should be. So it said this is a fix. It says you haven't loaded the tidyverse, but we actually did higher up, so that's not truly an issue. But then it does correctly note the missing NA remove argument and median, right? And so notes that we need to add that in. That was the other issue. It did correctly identify that. So kind of over-identified some issues, but then it's nice it even gave us this improved fixed version of the function. We don't really actually want to load the Tibble package here because we already load the tidyverse above. Generally, it's not good practice to load libraries within a function call. Okay, the reason being, users might be calling your function, and if they don't know an additional library has been loaded, that can create issues with masked functions. Essentially, the library makes a ton of functions available. It might overwrite or change R's default function that it's referring to without the user realizing that. So just typically it's best practice to load your libraries outside of functions at the top of your script. So this is not great, but it did correctly fix the NA remove argument and the end digits issue in the median calculation. So we'll give Copilot here a pat on the back. It did quite well. Okay. Although it's calling it Rust code, but it's actually R. Rust is a different programming language. Okay. So the last part of the activity I would encourage you to try out on your own, but it's optional, in which you'll create a print greeting function. Okay. But otherwise, this wraps things up for this activity on fundamentals of functions with R. Thanks, everyone.